Hello, welcome to another module in this massive open online course. So, we are looking at example problems, right. We have started looking at example problems for the Fourier analysis of discrete time signals, and we have started with example problems for the discrete Fourier series, alright. So, let us continue our discussion. We are looking at example problems for the Fourier analysis of DT signal, discrete time signals, and in particular we have started with the discrete Fourier series, alright, for discrete time periodic signals, alright. So, let us continue our discussion and let us look at the next problem. So, we have looked at problem number 1 yesterday, if I remember correctly in the previous module. So, let us look at the second problem, that is problem number 2, which is the following. So, we want to find the Fourier series of cosine pi by 2 n plus cosine pi by 2 n plus sine pi by 3 n. Naturally, you can see that these are periodic, and the period of this. So, this is a periodic signal, alright. So, this is your x n, and if you look at cosine pi by 2 n, the period of this can be found as follows: pi by 2 into k, or pi by 2 into n1, let us call this n1, equals 2 pi, implies, because cosine x is cosine x plus 2 pi. So, n1 equals basically 4, that is the period of the first signal. Similarly, for the sine signal we have pi by 3 n2 equals 2 pi, which implies n2 equals 6. So, period is of the first component, that is cosine pi by 2 n, is 4, and period of the second component, that is sine pi by 3 n, is 6, and the period of the sum, correct, is therefore the least common multiple, because it has to be a multiple of both, and therefore the minimum possible such length is the least common multiple of these. So, therefore, the period, fundamental period of this sum signal is n naught, which is the least common LCM of 4 and 6, which is 12. So, n naught equals period of x n equals LCM of 4 comma 6, the least common multiple of 4 comma 6, which is 12. Okay. And now I can write e raised to, now I can write using the properties of cosine pi by 2 n, using the properties of complex exponentials pi n by 3, I can write this as, this can be written as, well, e power j pi by 2 n plus e power minus j pi by 2 n divided by 2 plus e power j pi by 3 n, sin pi by 3 n is e power j pi by 3 n minus e power minus j pi by 3 n divided by 2j. Okay. So, therefore, this is equal to, well, half. Now, look at this pi by So omega naught, so if you look at omega naught, now the LCM n naught equals 12. So we have omega naught equals 2 pi over n naught equals 2 pi over 12 equals pi by 6. So pi by 2 is basically 3 omega naught. So omega naught is basically pi by 6. So pi by 2 is 3 omega naught and pi by 3 is 2 omega naught. Okay. So I can write this as half e power j 3 omega naught n plus half e power minus j 3 omega naught n plus 1 over 2 j e power j 2 omega naught n minus 1 over 2 j e power minus j 2 omega naught. And clearly you can see this is the coefficient of 3 omega naught, that is half. So, this is equal to C 3, this is C of minus 3, this is C of 2 the DFS, and this is C of basically minus 2. But C of minus 3, everything is modulo n. So, C of minus 3 is C of minus 3 plus 12, that is n minus k. So, that is basically C of 9, and C of 2 minus 2 equals C of minus 2 plus 12, that is equal to C of 10. So, this is basically, so what we have is from the above discrete Fourier series is C of 3 equals half C of minus 3, that is C of 9 is also equal to half C of 2 equals 1 over 2 j, that is 1 over 2 j, which is also you can write it as minus j over 2, and C of 10 is equal to minus 1 over 2 j. Okay, and therefore, I can write the signal as the discrete Fourier series representation xn as C3 e raised to j 2 omega naught n, as our C2 e raised to j over 2 omega naught n e raised to j 2 omega naught n plus C3, that is half e raised to j 3 omega naught n plus C9, which is half e raised to j 9 omega naught, C9 e raised to 9 j 9 omega naught n minus C that is plus C10, which is minus 2 j e raised to j 10 omega naught n. Okay. So, this is the discrete Fourier series representation of the, so this is the DFS this is the DFS representation of the signal xn. Okay. All right. Discrete Fourier series representation of the signal xn. So, that completes problem number 2. Let us look at problem number 3, and problem number 3 as follows. Let xn be a real periodic sequence. So, let us write it as this. Let us write it in compact form. Xn is real plus periodic. Okay. So, it is a real periodic sequence, and the DFS coefficient. So, given that the Z DFS coefficient is AK plus JBK. DFS coefficient CK can be expressed as AK plus GBK, and we want to find the trigonometric discrete Fourier series. Now, for this we want to find the given the discrete Fourier series, the discrete Fourier series coefficient is Ck, we want to find the trigonometric discrete. So, we want to find the trigonometric discrete Fourier series given the discrete Fourier series, the complex discrete Fourier series, or you can also say the complex exponential discrete Fourier series coefficient Ck. Okay. And let us also consider the scenario for simplicity where n naught is odd. Okay. So, let us consider the scenario where n naught equals odd, which also implies that n naught minus 1 equals even. Okay. Now, the discrete Fourier series is given as xn equals k equal to 0 to n naught minus 1 Ck e raised to jk omega naught n, which is, remember, n naught is odd. So, n naught minus 1 is even. So, this is C naught plus summation k equal to 0 or k equal to 1 to n naught minus 1 Ck e raised to j k omega naught n. So, n naught is odd, n naught minus 1 is even. So, I can write this as C naught plus summation k equal to 1 to n naught minus 1 by 2 Ck e raised to j k omega naught n plus C of n naught minus k e raised to j n naught minus k omega naught n. So, I am splitting it into 2. I am writing it, I am varying the index only from k equal to 1 to n naught minus 1 by 2. I am writing it as the sum of Ck e raised to j k omega naught n plus C n minus k e raised to j k n naught minus k times n. Okay. Now, if you look at this, since this is a real signal, this implies Ck and C naught n minus k, which is C of minus k, are conjugates of each other. So, Ck equals C minus k conjugate equals C n naught minus k conjugate. Okay. And further, if you look at e raised to j n naught e raised to j n naught minus k omega naught n, this is e raised to j n naught into omega naught is 2 pi, e raised to j 2 pi n into e raised to minus j k omega naught n, and e raised to j 2 pi n is basically unity. Okay. So, this is unity, and therefore, this is e raised to minus j this is e raised to minus j k omega naught n. Okay. So, basically what this tells us is that this is equal to, so I can write or rather recast xn as C naught plus summation k equal to 1 to n naught minus 1 divided by 2 Ck e raised to j k omega naught n plus Ck conjugate e raised to minus j k omega naught n. Okay. Now, Ck, now you can see this Ck conjugate e raised to minus j k omega naught n is nothing but Ck e raised to j k omega naught n conjugate. Okay. So, Ck conjugate e raised to minus j k omega naught n is basically C k e raised to j k omega naught n conjugate. Okay. So, now we have C k e raised to j k omega naught n plus its conjugate. So, basically what remains is what this leads to, it's twice its real part, twice the real part of C k e raised to j k omega naught n. Okay. So, this will be C naught, just simplify this will be C naught plus summation k equal to 1 to n naught minus 1 by 2 twice real part of C k e raised to j k omega naught n, and the real part of C k e raised to j k k omega naught n equals basically the real part of a k plus j b k cosine k omega naught n plus j sine k omega naught n, which is equal to the real part is will a k cosine k omega naught n minus b k sine k omega naught n. Okay. And therefore, substituting this, now you have x n, the trigonometric discrete Fourier series can be obtained as C naught plus twice summation k equals 1 to n naught minus 1 by 2 a k cosine k omega naught n minus b k sin k omega naught n, whereas I have already told you that this a k and b k are obtained from the DFS coefficient C k such that C k is a k plus j b k. So, these are given from the, these are basically the real part, a k is the real part and b k is the imaginary part of the DFS coefficient C k. Okay. So, a k equal to real part of C k and b k equals basically the imaginary part of C k. Okay. All right. Okay, and this is basically your trigonometric Fourier series, but remember when, also remember this is the trigonometric discrete Fourier series, but remember this is when n naught equals, n naught is even, sorry, or n naught is odd, sorry, n naught is odd. All right. Similarly, you can find the discrete Fourier series, the trigonometric discrete Fourier series when n naught is even. Okay. In that case, n naught minus 1 will be odd, so you cannot apply the same technique. Okay. All right. So, basically that brings us to the next problem, which is problem number 4, if I remember correctly. So, this brings us to problem number 4. Find the discrete time Fourier transform. So, now we are entering problems on discrete time Fourier transform. Let me just, we completed the Fourier series. These are the problems on DTFT. Okay, the problem on DTFT, this is number 4. Let us say xn equals un minus un minus n. What is the corresponding DTFT of this signal? So, this is un minus n minus 1. This implies, if you can see, this is clearly xn equals 1, 0 less than n less than equal to n minus 1 and 0 and 0 otherwise. Okay, this is your xn, that is it's 1 only in a window of 0 to capital N minus 1, and outside this window, that is for n less than 0, strictly less than 0, and n strictly greater than n minus 1, or basically n greater than or equal to capital N, this is 0. Okay. And therefore, x of omega, now if you find the DTFT, that is given as x of omega equals summation n equals minus infinity to infinity xn e raised to minus j omega n. Now, this is only non-zero from 0 to n minus 1. So, this is, and in that window it is 1. So, this is simply summation n equal to 0 to n minus 1 e raised to minus j omega m omega n, which is a geometric series, and the sum of this is 1 minus e raised to minus j omega n divided by 1 minus e raised to minus j omega, which is now, if you take e raised to minus j omega n by 2 common in the numerator and e raised to minus j omega by 2 common in the denominator. So, this will be e raised to minus j omega n by 2 minus, or in fact e raised to plus j omega n by 2 minus e raised to minus j omega n by 2 in the numerator, and in the denominator it will be e raised to j omega by 2 minus e raised to minus j omega by 2, which is equal to e raised to minus j omega n minus 1 divided by 2 times e raised to j omega n by 2 minus e raised to minus j omega capital N over 2. This is twice j sin omega n over 2. So, and you can see that the 2j factor in the numerator and denominator cancels. So, what you are left with is sin n omega by 2 in the numerator and sin omega by 2 in the denominator. Okay. Sin omega 2 by 2 in the denominator. Let us find the DTFT, or the inverse DTFT rather, of another signal. So, this is problem number 5. You have x of omega So, this is, remember, the DTFT is periodic. So, this is your pi, periodic with periodicity 2 pi. So, we have x of omega, this is your x of omega, which is equal to 1 as shown, magnitude of omega less than or equal to w, and 0 otherwise. This is in one period, or let us write it 0, w less than mod omega less than or equal to pi. Okay. So, basically this describes it in one period. This is, remember, this is also, because this is always a periodic signal. So, this is for a single period. This is for a single period. So, this is x of omega, the inverse DTFT, and what we need to do is we have to find the inverse DTFT of x of omega. The problem is, what is the inverse DTFT of this x of omega, which is 1 in this interval of width minus omega to omega. So, you can say this is a discrete Fourier time Fourier transform, which is the bandwidth of capital W. Alright, it is 1 in this band minus W to W. Okay. And the DTFT is given as, inverse DTFT is given as, remember, the inverse DTFT formula is x of n equals minus 1 over 2 pi minus w to w x of omega e raised to j omega d omega, which is equal to 1 over 2 pi. In fact, this is simply minus pi to pi. Therefore, this is 1 only in the interval minus w to w. So, this reduces to integral minus w to w, and in this interval it is 1. So, this is simply e raised to j omega n d omega, which is 1 over 2 pi e raised to j omega n over j n, evaluated between the limits minus w to w equals 1 over 2 pi e raised to j omega w minus e raised to, or e raised, I am sorry, e raised to minus e raised to j w n minus e raised to minus j w n divided by j n, which is 1 over 2 pi e raised to j w n. So, this is 2j sin w n divided by j n. So, removing the j's, the factor of 2's also go away. So, what we have is sin w n by pi n. So, basically that gives us x n, the inverse DTFT x n equals so this is basically the inverse DTFT of the inverse DTFT of the inverse DTFT of the given signal, alright, the corresponding in fact aperiodic time domain sequence. Alright, so we have looked at problems pertaining to the discrete Fourier series, and also the DTFT, started looking at problems pertaining to the DTFT in this module. Let us continue this discussion in the subsequent modules. Thank you very much.